Hi everyone! Today we're going to explore how machines actually read and understand text, and it all starts with something called tokenization. Two of the most popular tokenization models are Byte-Pair Encoding, or BPE, and WordPiece. Let's start with Byte-Pair Encoding. Originally, it was actually developed as a way to compress text files, but later OpenAI adapted it for tokenization when they were training the first GPT models. Today, BPE is widely used across many transformer models, like GPT, GPT-2, Roberta, BART, and DBERTA. As a quick reminder, tokenization is a process of breaking down text into smaller, meaningful pieces called tokens. These tokens can be entire words, parts of words, or even individual characters, depending on the tokenization method. Before we can apply byte-pair encoding, we need to prepare the text. This involves two key steps: normalization and pre-tokenization. Normalization means that we clean the text, things like converting everything to lowercase or removing any special characters. Pre-tokenization is where we split the text into smaller chunks, usually by spaces or punctuation. Once the text is cleaned and split, we extract all the unique words from the dataset. For example, let's say our corpus includes the words hug, pug, pun, bun, and hugs. These unique words are what we'll start working with in the next step. Once we have our unique words, the next step in byte-pair encoding is to break each word down into its individual characters. This is how we build the initial vocabulary. It's all the unique characters that appear in the dataset. For example, hug becomes HUG, pug becomes PUG, pun becomes PUN, bun becomes BUN, and hugs becomes HUGS. So if we list out all the unique characters, our starting vocabulary would be B, G, H, N, P, S, and U. This base vocabulary is the foundation that the BPE algorithm will build on in the next steps. Once we've built our base vocabulary, byte-pair encoding starts combining characters to create new tokens. This happens through something called merges. A merge is when an algorithm finds the most frequent pair of characters that appear next to each other and combines them into a new token. In the beginning, the merges are usually simple. They create tokens that are just two characters long. But as training continues, longer and more complex tokens can be formed. The BPE algorithm keeps repeating this. Find the most frequent pair of tokens, merge them into one new token, and repeat. Let's say these are the words in our dataset and their frequencies. Hug appears 10 times, pug appears 5 times, pun appears 12 times, bun appears 4 times, and hugs appears 5 times. When we start, we break each word into its individual characters like this. Hug becomes HUG, pug becomes PUG, pun becomes PUN, bun becomes BUN, and hugs becomes HUGS. From here, the algorithm will start finding the most common pairs and merging them step by step to build the final vocabulary. Now let's walk through how the BPE algorithm keeps merging tokens step by step. We start by looking for the most frequent pair of characters. In this case, the most frequent pair is U and G, which appears in hug, pug, and hugs, a total of 20 times. So the tokenizer learns its first merge rule: combine U and G into UG. When we update the vocabulary and the corpus, UG becomes its own token. Next, the algorithm looks for the most frequent pair again. This time it's U and N, which shows up 16 times. So now we merge U and N into UN. After this step, we look again, and now the most frequent pair is H and UG, which gets merged into HUG, our first three-letter token. We keep repeating this process, finding the most frequent pairs and merging them, until we build up a vocabulary of useful subwords that the model can understand and use efficiently. Now let's talk about WordPiece tokenization. WordPiece is the algorithm that Google developed to pre-train BERT, one of the most influential language models in natural language processing. WordPiece has since been used in many other models like DistillBERT, MobileBERT, Funnel Transformers, and MPNet. It's similar to byte-pair encoding and how it builds its vocabulary, but the way it tokenizes words is a little different, which we'll dive into next. Like byte-pair encoding, WordPiece also starts with a small vocabulary. It includes the alphabet, special tokens, and some basic symbols. But there's a key difference. In WordPiece, subwords are marked with a prefix, like double hashtag and BERT. This shows that the subword is part of a larger word. For example, the word word would be broken down like this: W, double hashtag O, double hashtag R, double hashtag D. Just like BPE, WordPiece learns merge rules, but the big difference is how it chooses which pairs to merge. Instead of simply picking the most frequent pair, WordPiece uses a scoring formula that looks like this. Score equals the frequency of the pair divided by frequency of the first element times frequency of the second element. This formula helps the algorithm prefer merging pairs where individual parts are less common. For example, a pair like "huh" and double hashtag ging would likely get merged faster because both parts are less frequent on their own. But a pair like "un" and double hashtag able might get skipped, even if it shows up a lot, because "un" and double hashtag able each appear frequently in many other words. WordPiece's scoring system helps create tokens that are more useful for understanding word structures across different contexts. Let's go through the same example we used earlier to see how WordPiece works step by step. We have the same words and frequencies. Hug appears 10 times, pug 5 times, pun 12 times, bun 4 times, and hugs 5 times. WordPiece splits the words into tokens like this. Hug becomes H double hashtag U double hashtag G. Pug becomes P double hashtag U double hashtag G. Pun becomes P double hashtag U double hashtag N. Bun becomes B double hashtag U double hashtag N. And hugs becomes H double hashtag U double hashtag G double hashtag S. We start with an additional vocabulary that includes all these pieces. The most frequent pair is double hashtag U and double hashtag G. But because double hashtag U is very common on its own, its score isn't the highest. Instead, the best pair to merge is double hashtag G and double hashtag S, which gives us a new token double hashtag GS. Next, we see that H and double hashtag U often appear together, so we merge them into HU. Then the next best merge is HU and double hashtag G, giving us the token hug. By following the step-by-step scoring and merging process, WordPiece builds tokens in a smart way that balances frequency and flexibility. And just like with BPE, this continues until we reach the desired vocabulary size. So why do we tokenize text at all? Tokenization is essential in natural language processing because it helps convert raw text into a structured format that models can actually understand and process. Here are 6 key reasons why tokenization is so important. 1. It helps control vocabulary size by breaking words into smaller, more frequent parts. 2. It improves generalization, helping models handle rare or completely new words. 3. It manages language complexity and ambiguity by splitting words into clear, manageable pieces. 4. It speeds up training and makes models more efficient by enabling batching and parallel processing. 5. It reduces out-of-vocabulary problems by breaking unfamiliar words into known subwords. And 6. It supports multilingual and domain-specific text, making tokenization flexible across different languages and specialized fields. Overall, tokenization is a crucial step that allows machine learning models to handle the richness and complexity of human language. Thank you so much for watching. I hope this video helped you understand how Byte-Pair encoding and WordPiece work, and why tokenization is such a key part of natural language processing.